So the lesson we're doing today, this is on page 6 of your unit handout, is called The Equation of a Line, Part 1. And Part 1, everybody, is going to be dealing with direct linear relations, and then tomorrow we'll look at the equation of a line for partial. So everybody think about when you have y compared to x. This is our y, this is our x. For direct linear relations, what does this graph look like? Have you got it, Daniel?
Does it go through the origin?
It does. So direct is a straight line, because it's linear, right? It's a straight line. But direct means it goes through the origin. So what we are doing today is learning how to find the equation of that line and use the equation to answer some questions. We've already done lots of work where we're using what we have done is we've had lots of practice dealing with direct linear relations. We've solved problems, we've done graphs, we've done tables of values, but now we're going to be using an equation. So the first example says in a car park in Red Deer, the cost of parking is $2.50 for every half hour. Complete the table and the graph showing how the cost of parking compares to the length of time you park. So it's $2.50 for every half hour. And there's a typing mistake in your handout. Down here it says 2.3. It should say 2.5. So make sure you change that to 2.5. So what is the cost for half an hour, for 0.5 hours? Well, it's $2.50. And I think when we complete this table, we're not really using anything complicated. We're just saying that every half hour is $2.50, which would mean a full hour would be another $2.50 or $5. And we're back to that thing that on the very first day when we talked about that cookie recipe and the number of cookies and the amount of flour, that if you set your table up so that this independent variable is always going up by the same amount, then your dependent variable will always go up by the same amount. This is going up by half an hour each time. And this is going up by $2.50 each time. So we don't need to use a complicated approach here. All we need to do is say, we're going to add $2.50 each time. Right? So we add another $2.50. And you can use your calculator to figure these out. We add another $2.50. We add another $2.50. We add another $2.50. So we'll pause there. Are we okay with getting that table completed? Okay, good. So now we want to make a graph. Well, one of the things on your assignment that you got back that some of you lost marks for is you forgot to put a title. So we need a title for this. What's the title going to be? The title is going to be cost compared to time. Remember, it's always y compared to x. The other thing is we should label the axes. I know that you've got a C up there on your graph and a T here, but we need to write the word cost and then brackets and put the units. And down here we need to write the word time, brackets, hours. And now we need to set up our numbers. We're going up to 3 hours. Just look up here for a minute. Don't worry about writing this next part down. But if I put 1, 2, 3. I think we can do better. You want to try to use as much of the graph as you can. So I think it would be better, and this is what you can write, to put 1 hour here, 2 hours there, and 3 hours there. Which makes this, of course, 0. Now what about the cost? If you look at your table, am I right in saying the biggest cost was $15? Yeah? So we're going to scale the axis vertically to go up to 15. And I think this works out pretty good. This is 5, 10, 15. Alexa, is this going to be a straight line? How do we know it's going to be a straight line? And you're right. How do we know that?
Because it's going up at a constant rate.
It's going up at a constant rate. We're back to that idea that every time you go up a half hour, the graph rises $2.50. It isn't that it's $2.50 for the first half hour and $2.50 for the second, and then all of a sudden the third half hour you get charged $20. It's the same amount per half hour. And that means, and I talked about this yesterday briefly, you don't need to plot all the points. You don't need to plot all the points. For example, in your table, everybody, you have, for time, you have 0.5 hours, and for the cost, you have $2.50, right? Now look up here. I don't want to plot that point because if I plot that point, I'm going to be sticking a data point in a place on the vertical measurement of the graph that's hard for me to locate. It's not exactly on the crosshairs of grid lines. So I think what I'll do is that. We know it's going to be a straight line. We don't need every single point. We just need a couple of points so we can draw the line with a ruler. So what's another one that we can put on here very precisely? Well, we could use this one, which is exactly at $10, or this one, which is exactly at $15. Let's plot the 3 hours, $15. There you go. So we're plotting 3:15. So if we know this is linear, and Alexa's saying it's linear and she's right, because every time you go up on the x-axis half an hour, you go up on the y-axis 250, it's a constant rate, then when you draw your line, 2 points is enough. Question for you. And we're back to the same question, which isn't a big deal, but I like you to think about it. Should we actually connect the dots? Well, you may not have experience in parking in lots, but I'll tell you right now, if they say it's $2.50 for every half hour, if I'm there for 1 hour, it's going to be $5. If I'm there for 1 hour and even a few more minutes, you know what it's going to be? It's going to be an extra $2.50. So it's not actually a line. When you draw this, you should probably draw a dotted line. Don't overthink that. I know you can get stressed over that. Don't worry too much about that. We'll keep coming back to it, and sooner or later it will click. By the way, remember this point that I said is hard to draw? Well, if we put it in here now, it's going to be on this line. 1.5 hours will be $12.50. 2 hours will be $10. 2.5 hours is $12.50. I guess this is $7.50 there, not $12.50. The point is, we didn't have to plot all the points. We just needed 2. So that's what it looks like. And what we're doing so far, everybody, is a question from last week. This is not new. We know how to do this. Any questions with the graph? Okay. Name the type of relation that's shown. It's a direct linear relation. How can the cost of the parking be calculated if you know how long the person parks? This is a new question. This is a new question, okay? What can you do to the time in hours to get the cost in dollars? This is a new question. We haven't talked about this yet. How many of you know what you would do to the number of hours to get how much you're going to pay? What are we going to do?
The number of hours multiplied by 250.
Not the number of hours times 250, because 250 is not the cost per hour, is it? How much is it per hour?
Oh, per hour, okay.
So it's only it's 250 for only half an hour, so how much is it per hour?
5?
Right. So the time multiplied by $5 per hour will give you how much you pay. And we can write that as an equation. We can say the amount you pay is equal to 5 times, I want to just look at something here, give me a second, times the time. Let's just check this out. Does that work? Take your calculator and take 0.5 times 5 and see if you get 250. Take your calculator. Well, I don't know that you need your calculator for this one. 1 times 5, does it give you 5? Take a minute and run down the list and just check to see if you multiply all those times by 5, do you get all those costs? It works. Okay. So now we have a formula, we have an equation, and that's the new part in today's lesson, right? If you look back at the beginning, I said we were going to be looking at solving problems using an equation. Well, we've come up with the equation. I hope everybody agrees that coming up with this equation isn't easy. It's not always going to be easy, unless you know the secret. Okay? Before I go on, I want everybody just to make a note that our cost is Y and our time is X. That's going to be important in a minute. Okay, let's get back to it. What's the slope of the graph? Okay. So we're going to find the slope using 2 points. It doesn't matter which points we use. Let's use this one and this one. So this is at 3, 15. This is at 1, comma 5. I hope that all of you know how to find the slope as soon as you have those numbers written down. Your slope will be equal to this y minus this y over this x minus this x. Which gives us
$5
$5,
per hour.
right, $5 per hour. Wait a minute. This is going to be the whole point. $5 per hour is the slope. Right? The slope is that rate that we said is the same. So what do we notice? So let me write down our answer here. Our slope equals $5 per hour. What we notice is this, and we're going to write it down and then I'm going to repeat it and ask us to think about what I'm telling you. What do we notice? The slope multiplied by x gives us y. When you multiply x by the slope, you get y. In fact, look at our table. Look what I've been writing in the table. This is x. We're multiplying by this, which is the slope, and we're getting y. Y is equal to the slope times x. This is what we notice. I mean, I can be more specific here to our example. Instead of saying y equals the slope times x, I could say cost equals the slope times time. But this is always the case for direct linear relations. Y will always be the slope times x. Always, 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 always. And this is what's at the bottom of your page here. Let me cover this up and go through it piece by piece with you. This is an equation for direct linear relations. When a graph shows a direct linear relation, the equation of the graph is always y equals mx. M is the slope. The equation is always y equals the slope times x. Y is the dependent variable. In our example, it was cost. X is the independent variable. In our example, that was time. And m is the slope of the line. What we're getting towards, what we're moving towards here, is not having to use a table of values and not having to use a graph to answer questions. We're working towards using an equation. All right, let's take a look at example 2. The table of values shows the relationship between air temperature and elevation above sea level. So let's talk about what this means. This is saying that when you are 0 meters above sea level, which means you're at sea level, the temperature is 0 degrees Celsius. I think this kind of makes sense to you. I don't want to turn this into a science class, but as you gain in altitude, the temperature drops. If you're on top of a mountain, it's cooler or colder than it is when you're at the base of the mountain. So this is saying when you're at 100 meters, the temperature is minus 1 degree Celsius. And when you're at 200, the temperature is minus 2. I have a question for you. Is this going to be linear? How do you know, Phoenix? It's the kind of thing that you just know looking at the numbers, but it's hard to put into words. Does anybody want to take a stab at putting it into words, why this will be linear? Daniel.
Because it goes up or down at the constant rate.
And I like that you said up and then you went, oh, up or down. It happens to be going down at a constant rate, right? So every time this goes up, every time the elevation increases by 100, the temperature goes down by 1 degree Celsius. So I want to just show this to you without looking at the graph officially. What this is saying is, every time you go up by 100 meters, this is the elevation. Every time you go up 100 meters, it drops 1 degree Celsius. Up 100 meters, drops 1 degree Celsius. Up 100 meters, drops 100 degrees Celsius, or 1 degree Celsius. So it's going to be linear. It's just that it's going to be going down. That's all. So what do we want to do here? We want to make a graph. So this is the elevation. We're going to add something here because I don't think I put it on there. This, oh, I did. I just don't have it here. This actually says elevation in meters on your handout, doesn't it? So I want to make sure you understand what we're looking at here. The x-axis is this line, and the y-axis is this line. Oops, there we go. So, what is the temperature at 0? 0. At 100, minus 1. At 200, minus 2. I think many of you are starting to get a real understanding here of why it's linear. If that rate is constant, then every time x changes by a fixed amount, y will change by a fixed amount. 300 drops again. Go up another 100 meters to 400, drops again. I want to make sure I plotted those correctly. Question for you. When we draw our line, can we actually connect the dots with a solid line? Sure. Can you be at 83 meters? What about 83.1 meters? You can be at any of these elevations, which means it is not just something like a number of logs, okay, or a number of cars. In Elijah's example, when he was talking about fixing cars, it was the number of cars. So that's what the graph looks like. Is it linear? Yes. This is linear, right? Is it a direct linear relation? Why? It goes through the origin, right? Starts at the origin. So because it's a straight line, it's linear, and because it starts at the origin, it's direct. So this is a direct linear relation. So is the relation linear? Yes. Is it direct? Yes. It is a direct linear relation. Okay, ooh, just a second here. We just finished saying that for direct linear relations, the equation is y equals slope times x. This is a direct linear relation. The equation of this line should be, and we're going to work on this together, the equation of this line should be temperature equals the slope times elevation. Because we learned in the previous example that y is equal to the slope times x. And y is the temperature and x is the elevation. So this should be the equation. Okay, I'm parking that there. We'll come back and talk about that. But I'm just making an observation. All right. What's the slope? So we need to pick a couple of points. I'm going to ask us to pick this point and this point. So we're going to write on here that this is at 100, comma, -1. And this is at 400, comma, -4. And we're going to calculate the slope using those numbers. So I'm going to freeze this on the screen on the right. So follow along very carefully. I'm going to take this y coordinate of -4 and subtract this y coordinate of -1. That's going to go on the top. Slope equals -4 minus -1. And if I do this y coordinate on the right minus the y coordinate on the left, then when I do my x, I have to go this x minus this x. So if I put -4 minus 1 minus -1, I have to go over 400 minus 100. Good? So be very careful here. This is an applied math class. We don't have to do things in our head. We've got calculators. Work out what -4 minus -1 is. -3. So we get -3 degrees Celsius divided by 400 minus 100 is 300. And that's meters. So when I divide those two, I get -0.01, I think. You can let me know. Is that right? Okay. Degrees Celsius per meter. Let's explain what that means. All right, explain the slope. For every 1 meter increase in elevation, the temperature does what? Decreases by how much? 1 degree Celsius. Sorry, 0.01. Right? Because it's per meter, not per 100 meters. That was my mistake. The temperature decreases by 0.01 degrees Celsius. All right, we're getting there. And the interpretation of your slope there is found just by looking at the units, right? Negative 0.01 degrees Celsius per meter. You go up by a meter, you go down by 0.01 degrees Celsius. What's an equation that describes the relationship between the temperature and the elevation? So I'm going to ask you, just see if you can figure it out. Does anybody have it? Perfect. I'm so glad none of you have it. I am. Because what you're all doing is thinking about this and trying to come up with an equation in your head, and I want us to not do that from now on. What is the equation of this line? It's direct linear relation. So this is the equation always for direct linear relation. Always, 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 always. In this question, there's no y. Nowhere does it say y. What is the variable that's on the y-axis? Look at your graph. Temperature, right? So that means temperature equals, what's the slope? Negative 0.01. I'm not going to put the units in there. That's the slope. And what's x? The elevation. That's it. That's all you have to do. Y equals slope times x. Let's try something. I'm going to go to my table of values. We said that y, which is the temperature, equals negative 0.01 times x, which is the elevation. Go ahead and take any of these and multiply by negative 0.01. You're going to get the temperature. So why are we doing all this? There's a reason. And it isn't just because it's a math class and we have to do math. There's a use for this. Because if we take a look at the next question, what is the air temperature at 239 meters? So just a second here. Let's make sure we understand this question. This is saying when the elevation is 239 meters, what's the temperature? Do you understand what it's asking you? Okay. So if I gave you that question and I gave you this table, then you would be trying to figure out somewhere in here is 239 meters. You would be trying to figure out what the temperature is. Do you agree you can't do that? Like, we can't just look at that and decide. Even if you looked at the graph and you go to 239 meters, this is 250. Do you agree 239 is in here somewhere? You could maybe read this and say negative 2.3, but it wouldn't be exact, would it? Because you're trying to locate those numbers on the graph. And it's not easy to locate them. But now that we have an equation, what was our equation? Temperature equals negative 0.01 E. Well, I can just put 239 in for E. So what I am doing here, everybody, is I'm putting this number here, and I'm going to calculate the temperature. The temperature will be negative 0.01 times 239. I'm getting, I think, negative 2.39 degrees. There's no way you could have got that accuracy by looking at the graph. No way. In this question, the elevation is 520, and what we are asked to find is the temperature. So we're going to use the formula, temperature equals negative 0.01 times the elevation. And you should get negative 5.2. Are we okay with that example, that question? We have one more to go. What if I did this? What if I said the temperature is negative 3.7 degrees Celsius? What's the elevation? Well, the formula is temperature equals negative 0.01 times the elevation. What we're going to have to do here, everybody, is put this in for the temperature and figure out, using the equation, what E is. And in this unit, we are reviewing some basic math as well. Let's just walk away from this for a second. If I told you 2x equals 40, how many of you know what x is equal to? This means 2 times a number equals 40. What's the number? 20, right? But how many of you know that it's just 20 because 2 times 20 is 40? Okay. What if it was this? Do you automatically know what you double to get 216? Probably not. So this is why in previous math classes you've been taught to get this x by itself, you divide both sides by 2. Remember this? So what happens is this cancels, and you're left with x equals 216 over 2, and you can certainly figure that out. You guys have calculators. I think it's 108. Okay. So why am I saying that? Because when we have this formula of negative 3.7 equals negative 0.01 multiplied by, sometimes we use just a dot for multiplication, E, and I want to get E by itself, I have to divide both sides by negative 0.01 to get rid of that negative 0.01. So I get the elevation is negative 3.7 over negative 0.01. And you can work out what that is. 370. Okay. And that would be meters. Listen, I'm aware that in this example, because the numbers are what they are, you could probably figure out the answers just by moving some decimals around, but it's not always going to be that way. That if it's 370 meters, it's negative 3.7 degrees Celsius. There's kind of a pattern there. Let's take a look at the next one, and then we're done. Well, in this question here, we're going to put negative 6.8 in for the temperature. How do we solve for E? Divide both sides by negative 0.01 and get E equals 680. So, summary. Prior to today, you knew that direct linear relations had graphs that looked like that. And this is y compared to x. Today, now you know the equation connecting the two variables is this. So if you can find the slope, then you have an equation connecting whatever the things are. Grams of flour and number of cookies. In fact, and the graph was, we had cookies here. Come on. We had cookies here and grams of flour here. And it was a straight line that went through the origin, and our slope was 4 grams per cookie. You can look back and see those numbers. You remember this? Okay. Well, I'm telling you that the grams of flour equals 4 times the number of cookies. Y equals the slope times x. So now that I have this formula, if I said, I don't want to make 20 cookies or 40, I want to make 68 cookies. Why? I don't know. But if I wanted to make 68 cookies, then I could put 68 in for n and multiply by 4 to get the grams of flour. It's a very useful thing. You have 2 examples to complete. 3 examples to complete for tomorrow on page 24 of your unit handout, number 4, 5, and 6. What you're doing is you're graphing data to determine the slope, to determine an equation to answer questions. I don't know if I'm going to expect you to get 4, 5, and 6 done. It may be in the next half hour or so that I tell you, you know what, just do 4 and 5, which will probably be the case. So get to work on that, please. I'll let you get settled in and get started before I come around to help you.